My name is Trey Wager. I'm an application engineer here at TechX. My presentation today will be covering a general workflow for using VSim and creating and running a simple simulation. Specifically, we'll be working through an example where we have made a crude approximation of a Wi-Fi antenna placed in the palm of a human hand and looking at some of the interactions involved there. So as a general outline, the purpose of this presentation is to introduce everyone to some of the VSim mechanics and the user interface, and to demonstrate a recommended and typical workflow. So to start off, we'll talk about the problem of the example and some of the basic settings that we'll be using. We will look at importing geometries, adding primitive geometries as well, and including all of the appropriate materials for those geometries. We'll look at the grid and some of the considerations that are important to look at when setting up the grid. We will look at an antenna signal and some of the SpaceTime functions we can use to get that working properly. And we'll look at some of the boundary conditions and the data collection that needs to be set up to get the right results and do some data analysis at the end. And then finally, we'll look at running the simulation, some of the settings that should be considered there, and finally analyzing the results in the end. So hopefully this will serve as a guideline for a good workflow to be used when you guys set up your own simulations for whatever you're trying to simulate. So the problem that this example will be addressing today, a situation that a lot of people encounter day to day, is holding an antenna in their hand. And what we want to answer is how the signals from this antenna interact with the hand, how do they penetrate the hand, and could various frequencies interact differently. And specifically, we're going to consider some of the frequencies associated with Wi-Fi signals in a cell phone. Now, typically, cell phones will use, for calls and text messages, the typical frequencies used are around 850 megahertz. But when we use Wi-Fi devices, you can typically choose between a 2.4 or a 5 gigahertz signal. Now, it's advertised that a 5 gigahertz signal will be much faster than the 2.4 gigahertz. However, the 2.4 gigahertz signal can have greater range because those longer wavelengths have a greater ability to penetrate materials and turn corners and go through doorways and stuff like that. And that's typically why you'll see in many Wi-Fi routers in your household the option to choose between a 2.4 and a 5 gigahertz signal. So yeah, so we will look at specifically the 2.4 and 5 gigahertz signals in this example and compare them here. So when you open a new simulation in VSim from scratch, you'll get a window that looks something like this. On the right, you will have your 3D view. This shows you your grids, your geometries. The axes are represented here with the red, green, and blue lines. Currently, the only thing in the simulation is a default grid in the axes. That is all that is seen here. And then on the left side, in the top left here, this is what we kind of refer to as the tree. This will contain all of the values that you will need to set in your simulation. Basic settings, constants and parameters, all the information regarding your fields, particles, geometries, histories. That's where you'll find all that information. And when you select each of those icons, the window below it down here, this is the property tab. This will show you all the properties associated with each of those things. So right here, we have the basic settings selected, and these are all the properties that can be found in the basic settings. On the right-hand side is the value for each of those properties, and you can edit those as you need to. In this case, We're going to look at the basic settings first through this workflow. We want to make sure that all of these settings are set correctly for our example. So we are looking at simulating electromagnetic fields. So we're going to want to use things like an electromagnetic field solver. And you also want to check some of these other things like the length unit, which in this case is set to meters by default, and that's what we want to use for the simulation. This is where you can change the dimensionality of your simulation to save time. For example, if you have a cylindrical simulation, you can change it to two dimensions. You can also change your coordinate system here. In this case, we'll be using a Cartesian 3D coordinate system for this simulation. So these are all the default settings that you see here. These are all perfect for this example. And this is where, so I definitely recommend checking this first before you dive into setting up the rest of your simulation. So now we can move on to the constants and parameters. These truly allow you to make a very powerful simulation that is very versatile and flexible for you to adjust later, and everything can update automatically. So the constants, they are what they sound like. These are all constant values that you can reference later when you're setting up your simulation. Some of these constants you see here, things like the elementary charge, electron mass, etc. These are constants that are built in and you will have available to you in all of your simulations. These other constants highlighted here, these are some of the constants that we have added for this simulation specifically. These are just some constants that we plan to reference later, so it's good to get these included right away. And then we have parameters as well. These are very similar to constants. However, they're even more useful in the sense that they can depend on other constants and parameters. So the way parameters work is that you can define them with an expression, again, that can depend on other constants and parameters. So for example, we have a period here, which is just defined as 1 over the frequency used. So for example, in this simulation, if we're moving, or if we're using a 2.4 gigahertz signal and we want to change it to a 5 gigahertz signal, when we make that change to frequency used, the period will update automatically. So with tools like parameters, we can really make sure that our simulation updates with every small change to various constants and things like that. So, cool. So those are all well, I should mention, in a typical workflow, it's not likely that you'll know what all of the constants and parameters are that you need to include right off the bat. So in this example, we already know what all of the constants and parameters are. When you guys work through your own simulations, you'll find that you'll be adding constants and parameters as you work through, including your geometries, fields, and all that. So just keep that in mind when you're working through your simulations. So now we have all that set up, we can start looking at the geometries. So whatever your simulation needs, geometry-wise, any physical things, waveguides, cavities, etc. I think it's important to get those geometries included early in your setup. In this case, we have a human hand that we would like to model, which can be difficult to create out of simple geometry like cylinders and squares, etc. So we're actually using a CAD model of a human hand that was likely created in either SolidWorks or Fusion 360. You can use whatever tool you like as long as your model is saved as an STL or a STEP file, or I believe we have a couple other file types we support, then it can be imported into VSim. Importing geometries is simple. You can just right-click on geometries here, select import geometries, navigate to your STL file you want to use. In this case, we had a hand.stl file. Selecting that file will open it up and move it into your simulation. So one thing that happens when you import a STL file is that it might not fit in the default grid that was loaded into the simulation. This happens a lot, and it brings up some other useful tools that are available to you. The first thing I'd like to bring up is the reset position button. So oftentimes you'll be zooming around, zooming in and out of your 3D view, or you might be panning around as well. If you do that and you lose your simulation or you just get lost, hitting reset position can allow you to bring everything back into view so you don't get too lost. The pop-up that you see here asks if you would like to resize the grid to fit the new bounds. So in this case, when it imported the hand, it's much larger than the grid that's currently there. So VSim's just asking if you want to resize the grid. I recommend saying yes to this. We will be editing the bounds of the grid later anyway. But for the sake of making sure everything fits appropriately, it's a good idea to hit yes to this prompt, for example. So after resizing the grid and clicking reset position, we can see our hand model imported on the right hand side there. So something else to keep in mind when you import your CAD models is the units that were used when the models were created. Typically in Fusion 360 or SolidWorks, a default unit of length is the millimeter, whereas if you remember from our basic settings, we were using meters here in this simulation. So you'll need to scale the CAD model here to make sure it all, it's in the correct units. So to scale the model, we can go into our geometries. We can find the hand geometry that we just imported. Selecting that, revealing the properties, we can see the scale here, and we can set that to the appropriate value to get the units correct. In this case, 0.001 is the scale we want to use. We also translated the hand just a little bit. We wanted to make sure that the origin of the simulation was near the palm of the hand. So we just used some other values here to translate this hand into the right position. Okay, so now we have our hand geometry imported, but to help create a slightly more accurate model, we also want to include some bones for the hand. I say slightly more accurate because we're just going to use some primitive cylinders to represent the bones of the hand. So to do that, we can actually show off another feature that VSim has, which is our primitive shapes that we can include. So in this case, if you right-click on our constructive geometry tab here, go into add primitive and select cylinders, you can create a cylinder and edit its properties to have whatever radius, length, position, and orientation that you need. So here we just went ahead and added 5 cylinders to represent each of our fingers in the hand and put them in the right positions within the hand model. Cool. So now we have our geometries. We just need to apply materials to these geometries. So VSim does have several built-in materials. However, 2 of them are not bone and muscle. So we'll need to include our own material file that has bone and muscle in that. To do this, it's quite simple. VSim just uses a file format with a .vmat extension. It's just a text file containing all of the relevant information. You can find more about this file in our documentation, or you can find the default VMAT file in your distribution of VSim, and you can tweak it as you need. So basically, you just set up a file that looks something like this. In this case, we have 2 materials, bone and muscle. They're both dielectrics, and then we can change all our values like the heat capacity, conductivity, permittivity, etc. So once that's all set up, we can go back into VSim. Under the materials here, you can right-click this and select Import Materials and find the file that you just made. and then you'll be ready to include those materials in your simulation. On the right-hand side, normally this is your 3D view, but if you click this database tab here, this will reveal hopefully the materials that you just imported into the simulation. So in this case, we have our bone and muscle. Highlighting both of these materials and selecting Add Simulation, we see both the bone and muscle materials populated over here in the tree. So now we are ready to add these materials to our geometries, which is also very simple. You can just come over to each of your geometries. In this case, we have all 5 of our fingers. And in the Properties tab, we can go to Material and select into this drop-down that will list all the materials we have available in the simulation at the moment. So in this case, we can apply the bone material to our thumb and the rest of our fingers. And for the hand geometry, we can apply the muscle material. And so we should be good to go there. So the next thing we need to consider is the simulation grid or the simulation domain to be used. And in this case, we can finally start to take advantage of those constants and parameters that we defined earlier on. So in this, so to set up the bounds of the grid, effectively, we really just need a grid that fully encompasses the hand and some of the area around the hand, so we can capture all of the fields that are emitted from the simulation. So we can take advantage, or these values were assigned as constants earlier on. So for x min, we can, or in this case z min, we can go to the value, right click it, and we can actually assign the constant to that value. And then we get a list of all of our constants that we defined before. In this case, we can apply the right value, which would be z min, not y min. But yeah, so that workflow is fairly simple. Just right-clicking values, and you can select your constant or parameter that you defined before. So that covers the bounds, and then we also need to set the number of cells in each direction, x, y, and z. In this case, the default is 3, 4, and 5. But we want to update that to a little more precise values. So in this case, when you're trying to figure out how many cells to include in X, Y, and Z, John touched on this in his talk earlier. It's important to make sure that you have small enough cell sizes that you capture all of the physics going on, but not so small that the number of cells in your grid just blows up and then your simulation becomes extremely computationally intense. So in this case, we defined a resolution that we're interested in. We set that as a constant. We chose a value of, I believe, 2 millimeters, which for a 5 gigahertz signal, the wavelength of that signal in free space is going to be around 6 centimeters. So a 2 millimeter signal or cell size is going to be much smaller than those wavelengths and should capture all the physics there. The wavelength will be smaller when it's in the hand itself, but 2 millimeters should still be smaller than that wavelength, so we should be good to go there. So using this resolution, we can take the size of the grid, just x max minus x min, divided by the resolution to get the number of cells that we want in each direction. So that's how we defined nx, ny, and nz, and we can apply those values to x cells, y cells, and z cells, similarly to what we did with the bounds of the grid. So now we have all of our geometry set up, the materials applied to them, we have our grid set up. We now need to start thinking about the antenna itself and the signal to use for the antenna. So to represent our antenna, or a crude representation of our antenna, we're going to need to use a couple different space-time functions. And space-time functions are a very powerful tool in VSim. They basically are functions of space and time. X, Y, Z, and T are all reserved variables in VSim. So what we can do, in this case, we only want to define a signal, a source signal for the antenna that varies in time. That looks something like this graph here on the right. Ideally, this would just be a sine wave at the frequency of the signal we're interested in. The reason we have this nice slow ramp up is that we want to make sure our simulation is as close to a equilibrium situation as possible, an equilibrium state. So we want to slowly ramp up the antenna signal over time and then allow it to oscillate after slowly ramping up. So to do this, we defined a few different STF functions. The first one is just the source, which is simply the sine wave at the frequency of interest. We then define a turn-on function. So this is a sort of complex function that depends on a sine squared and a couple of min and max functions that basically give us this orange curve here that just goes, so it basically goes from 0 to 1 in a smooth fashion and then remains at 1 for the remainder of time. And then we can multiply those two signals together to get this blue space-time function you see here. And so this is what we want to use for our antenna signal. Back in VSim, we can add space-time functions once again just by right-clicking on space-time functions, select add space-time function, and then clicking expression. It's good to point out here, we also have a lot of other options available to you as built-ins. And we also have a Python function as well. So if you really need to define something very complex or depend on some external source, then you can select this Python function and use a function defined in a Python script, which is very powerful. So in this case, though, we're just going to use a couple of expressions. We made our source expression and our turn-on expression. And then we just simply multiply the two together to make a turn-on source function, which we can apply to our antenna. So there's our signal. Now we just need to set up the actual antenna itself, which we will do with a very simple general distributed current. So here under field dynamics, we can add a current distribution by right-clicking on current distributions and then selecting the general distributed current. Here, we didn't bother with including conductors or anything that would be found in a real antenna. We are simply using an imaginary current distribution as a very crude approximation of an antenna with settings that look something like this. So we have our general distributed current, and we simply used a Cartesian 3D slab to represent our antenna. Very crude, but good enough to capture the physics that we're interested in. So here we have our X-min, X-max, etc. And we can see the antenna here in the palm of the hand. So that's going to be our antenna. And then to apply our signal to this general distributed current, as you can see, we have under the properties a J0, J1, and J2. Those are current densities in the X, Y, and Z direction. In this case, we want to use in the Y direction, so J1, we're going to apply the signal that we defined earlier. So if we right-click on value here, we can now assign a space-time function to this value and select the turn-on source that we defined before. So great. So now we have our geometries, we have our materials, we have our grid set up, and we have our antenna with a signal involved. So that's most of the physics that really needs to be addressed in this problem. Some housekeeping we need to do, though, is we need to include the correct boundary conditions at the edges of our simulation. In this case, since we want these signals to radiate out into space, We really just need open boundary conditions, although you can see we have many other useful boundary conditions that you may come across, depending on what you need. In this case, again, we're just going to be using the open boundary conditions, and we need to apply a different, or we need to apply the same open boundary condition to all 6 sides of our simulation domain. So that's the lower x, lower y, lower z, upper x, upper y, and upper z directions. So now we have all these boundary conditions in place. We should be good to go. All the physics is essentially complete, and we are almost ready to run this simulation. One more thing before we do that, though, this is to help with the analysis that we're going to do in the end. One of the things we want to calculate is, so since we're interested in the far-field radiation patterns, we're going to want to take advantage of a Kirchhoff box to calculate those fields. So to take advantage of this, we need to include a history, which going under history here and clicking add array history, we can add a Farfield box data. And this is going to allow us to include that Kirchhoff box, which we can use to calculate the far fields. This is also where you would go if you wanted to include histories of the fields in general. Let's say you just want to observe the value of the electric field inside of the hand, for example, at some point, maybe on the index finger. You can define a point on the hand and just record the electric field at that point throughout the entire simulation. This is where you would do that as well. If you had particles in a simulation, this is where you would record various features of the particles, their positions, energies, momentums, velocities, whatever you need, this is where you would find them. So in this simulation, we're just going to create a Farfield box data. Now, this Farfield box just needs to enclose the entire simulation, well, mostly just the hand that we're interested in. So in this case, we can use the values that you see here. This just fully encompasses the hand and the antenna, so it can capture all of the fields at the edge of this box, and we can extrapolate that out into any radius. The other thing we need to set here is the start time and end time for the box to record the data. Obviously, we don't want to start recording right away. We want to let the signal from the antenna propagate across the entire box and reach an equilibrium state or something close to an equilibrium state. And then we want to make sure we allow the box to record for enough time that any signals can propagate across the entire simulation domain since Farfield start. And that will give us the best results for a Farfield calculation. So Farfield start and stop were calculated as parameters as well. So once again, we can right-click the value next to start time and end time, go to assign parameter, and find the parameters that we set earlier. Okay, so now we have our setup effectively complete. So we are finally ready to run the simulation and start looking at some results. So here we have, so now that we're ready to run the simulation, we can come over here to the Run tab on the left-hand side, and we can look at a few more things we need to consider before hitting Run. The first thing is the time step. Again, this is similar to the grid in that we want to make sure we have find enough time steps to capture all of the physics and make sure we have a stable simulation, but we don't want to be so fine that we end up having millions of steps and this becomes a simulation that takes forever to run. So to calculate this time step, we simply considered the speed of light traveling across our simulation, and we wanted to make sure that light wouldn't travel across more than one cell in just one time step. So we chose a small enough time step to make sure that anything traveling at the speed of light, like our fields, isn't going to travel more than one cell. So that's how we arrived at this value. As for the number of steps, we chose enough steps so that the Farfield box can capture all of the information it needs, which came out to be around 3,000 steps, 3,500 steps or so. And the dump periodicity, this is just the period of steps. So how many steps you want to go by between every time VSim stores all of the information in the simulation. So I like to use a value that's about one-tenth the number of steps. So at the end of the simulation, I should have 10 dumps of all of the information that I can click through and make sure everything ran effectively in the simulation and there weren't any surprises there. This is also where you will set your how many cores you want to use to run the simulation and whether you want to run it in parallel or not. In this case, this is a pretty quick simulation, not a lot of steps. So I ran it in parallel with 4 machines, or 4 cores on this machine. This is obviously where if you have a more powerful computer, you can use all of the cores at your disposal and speed up your simulations tremendously here. But that summarizes what we need to do for this run tab here. And we are finally ready to click run and make sure everything works as expected. In this case, the engine completed successfully, which is printed down here. So we know everything worked well and we are ready to visualize the results and start taking a look at the data. So now we can click on visualize here, this icon here, and we can start to see the data that was recorded. So on the right-hand side here, this is your data. And to get a view that looks something like this, we can look at our tree. This is all of the data that gets recorded. So here I've expanded the scalar data. You can also look at the vector data of your fields. You can look at the meshes and geometries as well to see everything that was recorded. In this case, we just went into the scalar data and checked out the electric field. We looked at the magnitude of the electric field specifically. And normally this would just be a giant rectangle of one color, probably. But what we can do is we can slice the domain using this clip all plots option here. And setting x equal to 0, we can take a slice right through the center of the hand and the antenna to see what the fields are looking like here. On the bottom here, this is where you can pan through all of the different dumps that were recorded, which is basically stepping through in time. Looking at a particular dump here, we can see we have all of our radiation coming out from the hand. You can even see some of the signal penetrating the hand with those shorter wavelengths in that dielectric material. And we can start analyzing these results as well. So here's some of the visualization. If we move into the Analyze tab, this is where we can do our analysis of the far field radiation patterns. So there are several analyzers that come with VSim. Many of them are simple, some of them are more complex. In this case, we'll be using the Compute Farfield from Farfield Box analyzer. So this opens up this view here on the right. We have a number of parameters that we can set when we do this calculation. Most of these are the default values. In this case, we just want to look at the electric field here. We want to consider a radius 10 meters away. The frequency, in this case, when I was running this analyzer, I was looking at the 2.4 gigahertz signal. The number theta and 5 points, this just makes sure that we have a nice high resolution output in the end. And then we can go ahead, click Analyze, and run this analyzer. So this will do its thing. This will create a couple more data files that we can visualize back in the Visualize tab, which we can look at. So heading back into the Visualize tab here and clicking Reload Data. That's important because we need to get the data that was just generated by the analyzer. So reloading the data, you'll actually find that you have another piece of scalar data to look at. And so selecting this is the power of the Farfield data here. We get a result that looks something like this on the right. So here we have this interesting large lobe in the Farfield data that's being emitted from the palm of the hand. And interestingly, through the hand, you can see it's clearly being attenuated by some amount, which is interesting. This is what we're interested to see. And this is the 5 gigahertz signal here. So now the powerful part of using all these parameters and constants is that we can go back to the setup tab and we can change the frequency used from 5 gigahertz to 2.4 gigahertz, save the setup, and rerun the simulation. Everything should update automatically for you. Rerunning the simulation and redoing the analysis, we can visualize the results for the 2.4 gigahertz signal as well. And that's what we see here. So same exact analysis, same simulation, just with that different frequency, we get a Farfield pattern that looks a little more like this. So you'll notice it's a little more smooth. We still have a very large lobe on the side that's being emitted from the palm of the hand. But we also have a considerable lobe coming through the hand as well. It's much larger than the one for the 5 gigahertz signal, especially. And finally, we can compare these two side by side, and we can see that the 5 gigahertz signal is clearly more strongly affected by the presence of the hand, whereas the 2.4 gigahertz signal, not so much. So this is really interesting, and bringing it back to what those advertisers or to what they claimed about the 2.4 and 5 gigahertz Wi-Fi signals. Perhaps the 5 gigahertz signal is faster, but their advertisement that the 2.4 gigahertz has stronger connections and range is definitely supported here. Looking at the 2.4 gigahertz signal, it clearly has a greater ability to penetrate through the hand, and especially is more uniform of a distribution, which I think is pretty interesting for such a simple simulation with crude approximations of things like a human hand and an antenna, that we can get results that seem this good, this positive. Okay, so that is a example of a workflow that was used to make this simulation, from the setup to running to doing an analysis. This is a good workflow to follow, and one that I recommend. So yeah, I can answer any questions. I think I have one that I missed, most likely.
Looks like we have a question from about boundary conditions.
Why XYZ and XYZ? We have, so in the simulation here, in this example, we had a boundary condition that needed to be addressed for each side of the simulation domain. So for any Cartesian 3D slab, you'll have a lower upper X and lower and upper Y, lower and upper Z. So that's why we have 6 boundary conditions for this simulation domain.